Welcome once again to Captain's TV. In the previous tutorials, we studied how to name simple carboxylic acid compounds. And today we're also going to look at the acidity of carboxylic acids. Carboxylic acids, they are acids. That's why they are named as carboxylic acids. So let's take note of that. The acidity of a compound is defined as the ease of loss of a proton. So when any compound, there's a compound A has a proton somewhere, and that compound A can easily lose this proton to another compound, then this compound A is termed as acidic. Carboxylic acids in bases or aqueous solutions are able to donate these protons to a base, or let's say in aqueous solution. That's what defines their acidity. They are able to lose this proton to a needy compound that is in need of a proton. That defines the acidity of carboxylic acid. And the strength of, or the ease at which this proton can be lost, depends on the environmental factor around us. The electron density of this whole molecule. So let me say, if the bond between this oxygen and this hydrogen, if this bond is very strong, then it means an incoming base, let's say water, can hardly take this. It will take it, but it will hardly take it. If the bond between these two atoms is very strong, then a base can hardly take it. In other words, if the bond is very weak, then the base can easily take that hydrogen. So the ease of the taking of this hydrogen depends on the number of factors. That is the number of electron withdrawing group attached to this molecule. If this molecule has several electron withdrawing groups, that is atoms of higher electronegativities, then it means that those atoms are going to pull out electron density of this oxygen, hence making this bond very weak. Therefore, an incoming base can easily take the hydrogen. Let's say we have this molecule and another molecule, the same molecule, having an electronegative atom, like let's see fluorine. Fluorine is a very electronegative atom, and in fact it is likely to be the most electronegative atom on the periodic table. Now, because of the pull exerted on this environment by this fluorine, the electron density at this area is going to be less as compared to this side. So therefore, because of this presence, we are going to have more electrons here than here. And bear in mind, this oxygen just needs more electrons so as to balance the positive force of this hydrogen. So therefore, if this side is deficient of electrons, it means comparing this one and this one, the strength that this oxygen will get to bond to this hydrogen here is going to be less as compared to this side. So here there's going to be a strong force between the oxygen and this one as compared to here. This side is going to be weak bond between this oxygen and the hydrogen. And here there's going to be a strong bond between this oxygen and this hydrogen. The reason being that here this fluorine has what? Decreased the electron density, that is the number of electrons around the system. Therefore, there's going to be a strong force of attraction here than here. Now, if you have strong force of attraction here and here, it means any coming molecule that is in need of this hydrogen coming to take it will hardly remove the hydrogen from here than here. So if the molecule can easily remove the hydrogen from this side, then it means that this molecule is highly acidic. If this molecule can easily lose this hydrogen, then it means it's highly acidic. It is highly acidic because one, this highly electronegative atom fluorine has decreased the electron density of this environment and thus has weakened the bond between this oxygen and this hydrogen. In other words, a base or an incoming base will easily remove this hydrogen here than here. That is to say that when you have a molecule with a substituent, an electron withdrawing molecule, that molecule will increase acidity by decreasing the electron density of the carboxylate group. Differences in electronegativities also account to acidity of molecule. So you have fluorine, you have somewhere here bromine, the same molecule, these two molecules, and you are to compare their acidity. This one too is electron withdrawing and this one too is electron withdrawing. But the acidity of this one is going to be still greater than this. The reason being that this atom fluorine is highly electronegative as compared to this one. See, when you check the periodic table, halogens, this fluorine comes and this one is down. So this fluorine is highly electronegative as compared to this bromine. So it can pull more electron from the carboxylate group than this. In other words, it can weaken this bond than this one. Now, if this one can weaken this bond than this, in other words, this one can easily be removed. That is to say that this one becomes more acidic than this. Position of the atoms also account for electron acidity. Let's say you have this one and this fluorine here too. Though it's the same molecule with the same substituent, yet their positions, how close they are to the carboxylate group, also account for differences in electronegativities. Because this one is still closer to the carboxylate group, this can take more than this. This one exerts a force which we call an induction, a force to pull an electron from this side. Now, because of its distance from the carboxylate group, it will exert less force on this as compared to this one. Hence, this one becomes more acidic than this. So if here is A and here is B, the B will become more acidic than A. Let's look at another instance. When now here is, we have two fluorines here. Sorry, one fluorine here as usual as we used. And here now we have two fluorines here. Now they are all fluorines and they have the same electronegative strength, but here they are okay in double and here it is single. If here is double and here is single, then it means that the force, the induction force exerted on this one is going to be greater than this. So this one will become more acidic. Hope it's clear. This one exerts more force of induction, more electron withdrawing force on the carboxylate group than this because they are two, double. And here's only one. So the more electron pulling exerted on this carboxylate group than this. If there is more electron pulling strength on the carboxylate group, it makes that one more acidic. So compound A in this instance is more acidic than compound B because it has two fluorines that are pulling electrons from this side. When they pull, as I said earlier, they will weaken the oxygen-hydrogen bond here. Hence, an incoming base can easily take this hydrogen, leaving the oxygen easily than this. Thank you very much for watching this video. Kindly like and subscribe to this channel as we are going to drop more videos on reactions and other substance based on carboxylic acid, as well as other organic molecules. Please like and subscribe to this channel. Thank you very much.